Good morning, boys and girls. Today we are going to do a revision on the rates of reactions, and we are going to be answering typical examination questions. But to help you understand what is happening with this experimental approach, we are going to actually perform the experiment here and carry out the determinations which we are supposed to do. So I'm going to repeat this experiment as it is here. I don't have a balance though, but yeah, it's not going to be much of a problem. I'm going to approximate the masses which we are going to use. And as for the cotton wool plug, I'm going to use a soft tissue to block it over there. So I'm going to put 50 mils of dilute hydrochloric acid. So you are going to see that this is my calculations I've done to dilute hydrochloric acid from a concentrated solution of 18 molar. So we use C1V1 is equal to C2V2. So the actual quantities I'm going to use, I'm going to dilute 18 mils of concentrated hydrochloric acid to 1 molar. And I'm going to make 100 mils of my solution. So 100 mils converted to dm cubed, it gives you 0.1 dm cubed. So if I do my calculations very well, I make V1 subject of the formula. So 18 molar comes this side to divide it. So if you say 1 times 0.1 divided by 18, it will give me a certain value which I'll multiply again by 1,000 to find the cubic centimeters which I am going to measure from a measuring cylinder and transfer it into a 100 ml volumetric flask. So my solution of 1 molar hydrochloric acid is this one. And I'm going to transfer 50 mils of this solution into a 250 ml conical flask like this. Okay, my 50 mils goes down to there. So I'm going to keep on adding like that, yes. So I now have my 50 mils of my dilute hydrochloric acid in a clean conical flask like this. So I'm going to approximate the size of the magnesium ribbon. So here we are saying 2 experiments are carried out to investigate factors that affect the rate of reaction between magnesium and dilute hydrochloric acid. And this is the balanced equation we are given, which shows that magnesium solid reacts with aqueous hydrochloric acid to give us magnesium chloride and hydrogen gas being bubbled out. So, ladies and gentlemen, boys and girls, this is a piece of my magnesium ribbon. It's a very tiny piece, but yes, you can see it like this. So I'm going to drop it into this reaction, into the solution. And then we are going to look at our clocks and time, how long is it going to take for this ribbon to completely dissolve. I'm not going to stir it, I'll just drop it and then close it with a, like that. So there we are. If you take a closer look at the ribbon, you can actually see some bubbles coming off where the ribbon is sitting. You can actually see what's happening there. So the ribbon is reacting. It's actually dissolving in there. So it satisfies what we are seeing here on our balanced equation, where we are saying magnesium sulfate, magnesium solid, reacts with hydrochloric acid to give us magnesium chloride. So this is a salt which is dissolved in the solution. And then the gas we are observing there is the hydrogen gas being produced. So, boys and girls, look at our magnesium. It's gone. It's no longer there. And if you check how long did it take for the magnesium ribbon to react there, it takes less than a few seconds. Okay. So that was a ribbon. So I'm going to throw away this and put a new solution, and then I will use magnesium powder. So yes, this is fine magnesium powder. Let me put it here so that you can actually see how fine it looks like. It's very fine powder which is finely ground, and it's a metallic gray in color, as you can see. Okay. So I'm going to throw away this solution, and I'm going to rinse my flask. I'm going to rinse my flask. There we are. And then if I put these 50 mils, the remaining 50 mils of this. Right. So, just to repeat the observation we made on the previous experiment, we saw that when I put in the magnesium ribbon there, it floated for a while on the surface before we started seeing some bubbles coming up, and the bubbles were coming slowly until they vigorously were liberated from the solution. So I want you to make a quick observation of what's going to happen when I put in the powder. Is the powder, magnesium powder, going to is it going to be suspended on the surface there for a while before we start seeing any reaction taking place? So those observations are going to determine what's going to happen here. So under normal circumstances, we are supposed to have a stopwatch where the moment you drop in your magnesium, you start the reaction, and then immediately when everything disappears, you stop. And then you use your time frames to determine which reaction is taking place faster than the other one. So I want you to look at this. I'm not going to stir this the solution when I add my magnesium. So I'm going to take a tiny little scoop of the magnesium powder. So you saw how small my ribbon, which I put in there. So I'm going to use a tiny little scoop of this. I want you to observe what's going to happen as I add the powders into the solution. There we have it. I'm trying to keep track of the powders, but it looks like immediately when they touch the surface of the solution, they are disappearing. Look at the bubbles. So within a second, they are gone, nothing. Let me keep on adding. Maybe my solution is concentrated enough. So look at this again. If I look at this, Within a second, they are gone. See? So you see, the solution is beginning to turn milky. I will tell you why. So I still have a lot here. I can put all of it in and see if it is going to change anything. I want to see if I'm going to have a thick gray powder suspended on the surface. Nothing. It's all gone. And you can actually see the hydrogen gas being given off. You can actually see it as I'm steering it and driving it out like this. If I'm to take a glowing splint and put it here, you will hear boom, a popping sound to show that the hydrogen is burning. So there we are. So what we are observing here is that the nature of your materials affect how reactions take place. So in this case, you see that if you make your material in the powder form, it will react very fast, unlike when you keep it in a crystalline form or when it has got large particles. Okay, so let's answer this question technically, what you are expected to put down as an attempt to answer the question. So having made these observations, you should now approach this question with a clear mind. I know in some schools you don't have all this equipment to do the experiments, and some of these diagrammatic representations alone, they do not make much sense to you. But after having seen this experiment, you can at least understand what's happening. So let's study this diagram and compare it to what we have seen there. We had our cotton wool plug. I used a tissue to prevent the hydrogen from escaping. We used dilute hydrochloric acid, and then we saw the gas bubbles coming off the solution. And you saw when I put my magnesium ribbon, how it settled for a while and gradually dissolved into the solution and bubbles being generated. Okay. So from that information, can we make sense of how we apply our knowledge on rates of reaction? So here we are. If you take a look at this, this is question 5 of paper 2, 2018, May, June. So the instruction is saying in experiment 1, a certain mass of magnesium ribbon reacts with excess dilute hydrochloric acid. In experiment 2, magnesium powder of the same mass as the magnesium ribbon reacts with the same volume of excess dilute hydrochloric acid. So the concentration of the acid is the same in both experiments. So you actually saw that I used the same solution. I didn't change anything. So the same solution of 1 molar hydrochloric acid, which I diluted from a concentrated solution of 18 mol in 100 mils. Okay. So we are saying the apparatus below is used for the investigation. This helps you to understand what exactly is happening, and we expect you to be able to attach an intelligent interpretation of what is happening there. Okay. So here, when they say define reaction rate, so from what you have observed, what would you think the reaction rate is all about? Right, so it says that define the reaction rate. So you can actually see that from our observations, it's a measure of how fast or the speed at which a reaction takes place. So in this case, you can actually see that the technical response which we are expected to put down for 2 marks, it's a little bit detailed, which enables you to understand what's happening with this rate of reaction. Okay. So we are saying that with a rate of reaction, it's just a measure of the speed at which a reaction takes place. So what we have observed is that some reactions take place slowly, while others take place very fast. So if you put them together in a technical term, we are saying a rate of reaction is it's simply a measure of the speed at which a reaction takes place. Now, so for this investigation, write down an independent variable. What is it that we call an independent variable? It's something which does not vary. That's what we refer to as an independent variable. So like in this case, something which is independent here about the materials, if you look at them, what we were comparing, the powders versus the ribbon. So a ribbon has got a very small surface area while the powders exhibit a very large surface area. So in other words, we can refer to the independent variable as the surface area or a state of division. And then what would you write down as the control variable? So a controlled variable is something which is a constant, which does not change. So if you look at our reaction instruction here, we are saying that use the same volume of excess dilute hydrochloric acid. So the concentration of the acid is the same. So since we are saying the concentration is the same, that's a control variable, because we are saying under the same concentration, we are observing different reaction behaviors. Okay. So to move on with the example, so you can see that for those observations, you get 4 marks for that. Okay. So the change in mass of magnesium is calculated and recorded in 2-minute intervals for both experiments. So the results obtained are shown in the graph below. Okay. So let's study this graph in details. You can actually see that this is a measure of the mass of magnesium in grams versus time in minutes. So the mass was, we can approximate this to something like 3 grams, and then at time 0 it was 3. So this is for experiment 1. You can actually see that the mass was decreasing slowly per unit or over a 16 minutes period. But for experiment 2, see how quickly the mass was dropping, and within 10 minutes all of it was reacted and gone. It was all gone in 10 minutes. But for experiment 1, it took 16 minutes to react all the magnesium ribbon. So clearly this graph shows that this is the magnesium ribbon while this is the magnesium powder. So let's use our interpretation of this graph to answer the questions. So here we are. They are saying use the information on the graph to calculate the volume of hydrogen gas produced in experiment 1 from T2 minutes to T10 minutes. Okay. So for us to determine the volume of hydrogen gas produced in experiment 1 from T2, how are we going to make use of this information to answer that question? So you are expected to know how to carry out a few mathematical calculations here, which will enable you to understand what's happening. So you can actually see that the calculations are simple and straightforward. So you can actually extrapolate the information from the graph here. So you see that from time t is equal to 2, the mass of magnesium was 2.6, right? And then from at time t is equal to 10 minutes, the mass of magnesium was 0.2. So we are going to make use of this information here, where we are saying at t is equal to 2 minutes, mass is equal to 2.6 grams, okay? But when t is equal to 10 minutes, the mass is equal to 0.2 grams. So the change in mass of magnesium, change in magnesium, so I'll say change in the mass of magnesium is equal to 2.6 grams minus 0.2 grams. So this gives you 2.4 grams. Okay. So, and what is the time change here from 2 to 8? So it's over a period of 8 minutes. Okay. So when we have got this mass, so we are saying that the number of moles of magnesium, N, is equal to mass over relative atomic mass, which is equal to 2.4 grams over the relative atomic mass of magnesium is 24 grams. Okay, so the number of moles is equal to 0.1 mole. Yes. So 2.4 divided by 24 is 0.1 moles. Okay. So now if you look back at the equation here, you can actually see that 1 mole of magnesium reacts with 2 moles of hydrochloric acid to give us 1 mole of hydrogen gas. So the mathematical ratio is 1:1. So if it is 1:1, we are saying the ratio of magnesium to hydrogen gas is such that for 0.1 moles of magnesium, we will also get 0.1 mole of hydrogen. But the question is asking us, about calculate the volume of hydrogen. So for us to determine the volume, we know that if this number of moles of hydrogen is equivalent to the amount of hydrogen which has been produced there, of which we know that from our concentrations, we are saying concentration is equal to number of moles over volume. Okay, so we want to find the volume. So it means that we can find volume by making V subject of the formula. So where we will say V is equal to number of moles over concentration. Okay. So we now know that our volume, our number of moles is 0.1, and then the concentration of our solution, we diluted this to 1 molar. So we plug in our values and say for V is equal to N over, and our concentration is equal to 1 molar. So, or let's say mole per dm cubed. Mole per dm cubed. So we are going to say our volume is going to be equal to 0.1 mole divided by 1 mole per dm cubed. This and that, they cancel each other. So your volume is going to be equal to 0.1 dm cubed. Change it to cubic centimeters. It gives you 100 cubic centimeters. Okay. So that applies to our calculation we have done here. But in the experiment, depending on how much volume you have used, you can find a different value there, but the calculation is the same. I've used this information directly onto our calculation because we used 100 mils and also we used 1 molar solution. Okay. So, we are actually given the information here. They say that take the molar gas volume as 25 dm cubed per mole. So if we are going to use a 25 dm cubed per mole, so it means we are saying for V is equal to N over C. So if we are told that the molar volume is equal to 25 dm cubed per mole, so we'll say if 1 mole is equal to 25 dm cubed. What about 0.1 mole? Is equal to what? So this becomes simple ratio where we cross multiply things. So this will become 0.1 times 25, which gives you 2.5 dm cubed. Okay, so this will be your answer given this information we are working with. Okay, right. So for 5 marks, you get that. So the next part is asking you to calculate the initial mass of magnesium used in the average rate formation of hydrogen gas. So you are told that the average mass here is 2.08 times 10 to the power minus 4 moles per second. And you want to determine the initial mass of magnesium used in the average rate of formation of hydrogen gas in the experiment. So this is a very simple and straightforward manipulation we can do here, because we know that the average rate is equal to change in the number of moles over change in time, where we are saying the change in number of moles, we have observed that the rate here, which is represented, is 2.08 times 10 to the power minus 4 moles per second. So if we are to replace that, to put it here, it's going to be 2.08 moles per second is equal to change in the number of moles, which we don't know, over the change in time. So we saw that our time changed from 0 to 10 minutes, meaning that if we change 10 minutes to seconds, it's going to be 10 times 60 seconds, which gives you 600 seconds. Okay. So now, for that, we make our change in the number of moles subject of the formula. So we multiply this by that. So if you multiply 2.08 times 600 seconds, you get your change in N, which is equal to 0.125. 0.125 moles. Okay. But does it end there? We are saying if this is 0.12 moles, so what about the amount of magnesium which we use there? So we are saying the mass of magnesium is equal to the number of moles of magnesium which we have used. So so it will be actually the change in the number of moles of the magnesium. So this is going to be equal to 0.125 moles times the relative molecular mass of magnesium, which is equal to 24 grams. So if you punch this into your calculators, you will find this as 2.995 grams, which is equal to 3 grams. Okay. Now, finally, or lastly, they are saying use the collision theory to explain why the curve of experiment 2 is steeper than that of experiment 1. So if you come back here and look a closer look at this, you see that this curve is more gentle, but this one is quite steep. So using the collision theory, we agree that materials will only react if their surfaces of contact are larger and they've got frequent collisions. So you'll see that when we were using a ribbon, most of the materials were trapped inside the ribbon and their surfaces were not readily available for them to react. So that's why the ribbon reacted slowly, and hence its curve, diminishing curve, is quite gentle. But for the powdered magnesium, the tiny little particles have got a very large surface area, such that they were randomly and rapidly colliding with the molecules of the hydrochloric acid. So for that reason, they reacted rapidly, and hence they got used up very quickly, and their masses the mass disappeared so rapidly. So this is how we expect you to answer these typical examination questions, and from your understanding of what happens right from the experimental part, putting together your interpretations of the reaction process itself, and then you make use of your information to answer all these questions. So you see that all what we have done there is 17 marks. So you can actually do this faster in an exam, having all this background information and the technique of interpreting experimental data. So when we meet next time, boys and girls, we are going to talk about equilibrium, where we will also do a small experiment and use the experimental data to answer a typical examination question like this. Thank you very much. I hope this clears a lot of misconceptions of how to address a typical examination questions. Enjoy.